Hi, this is the amazing relationship of gravity and Boltzmann constant. Gravity as Planck's constant to the cube root, and Planck's constant to the 2/3 power, so directly related. If you take those three combinations, you have the identity gravity, Boltzmann, and electrostatic. And if you put that on an exponential scale, they line up perfectly. Now, to do that, you have to actually off them by 3/2 and 8, which is 2 to the 3rd power. And that's easily understandable. But when you do that, you get a r squared of 0.9999. Those must be related. There's no way you can have things that closely related with that much correlation unless there's some underlying physics. And let's talk about what they are. So for me, I take this back and I use Mac Gregor from Livermore Labs, a great scientist. And he published a number of things, including the story of alpha about the fine structure constant. Now in his work, they basically determined various elementary particles based upon the lifetime for them to settle back into a non-excited state. And guess what? He found that those were all related to a power of the fine structure constant called alpha. And what I do is I relate the fine structure constant to the root, the square root of the particle edge divided by the Bohr hydrogen radius. And that's a physical model. And that means it's one strength at maximum at the particle edge, and then it gets smaller and smaller and smaller. So if you take charge at the particle edge, it's a big number, and you reduce it by that ratio over squared, and you get Planck's constant. That's the one we're using up here at the top. Planck's constant as the basis is really based upon the electrical charge, the strength of the electron at the Bohr radius, which is the basic equilibrium. So now he did this great graph, but I took it one step further. You can see that there are clusters around various important numbers for the exponent. So 0 exponent is the identity, okay? The 1, the 2, okay? And then it keeps going up. And you would think that that's just not applicable, but guess what? That number is 2.666. But remember, my exponent was by half, okay? That half appears all the time. That means that this number, the mass of an electrostatic function and the release time at the square root, at the cube root, depends upon 2.66. But if you convert it to my thing, it's going to be 1.333, 4/3 to the power of 4/3. Wait. In my schedules, I've got a 1/3 and a 2/3. And that 1/3 is the extra over 1. So gravity is this omega particle versus Planck's constant. Or one over the other is a subtraction of the exponent. Now, doing this scaling then gets you the 4/3 and gets you an excess amount of 1/3. That's the main point of what I'm trying to say here. Now, how do you get to that? Well, in part, this also goes to mass. And what you find is that mass is also related to these two fields in equilibrium. This electrostatic field and this extra 1/r, angular momentum, omega, or tau, or hypercharge, or 100 other names that we've used for different things, but they all sort of have the same concept, and that's an extra 1/r, which was great math from Bohr, but the wrong physical model, obviously, as an orbit and angular momentum because it's not moving, okay? It is just something with an extra strength versus electrostatic, and opposite. That's why you subtract them. So when we do this, we take exponents and they become effectively at different comparisons. The equations are 1/distance cubed for a field, and of course 1/distance squared for the Coulomb schedules. So basically that's a 3/3, which is 1, and so no translation is required for electrostatic, all the bases. But when you get a hypermeson or angular momentum, you get 1/distance to the 4th. And the transition from that becomes that distance, because you're always referencing it to that equilibrium state, which is the point of transfer where both are equal, because you get that proton, one electron equality. Now, x as 1/3 is also a different field. So now you've got the hypermeson at 4/3, but gravity is 1/3. So it's a net, it's a mixed constant. It's Planck divided by the extra 1/r. So you get this extra factor. So what happens is, well, mass is trying to figure out both of those two fields scaled at 1/distance cubed. So the exponent there becomes 1/6. And if you calculate the translation of that, there's that factor of 3/2, which is the math of an integral of 1/distance cubed versus a integral over the 1/distance to the 4th. Obviously, as you're doing this conversion, you end up throwing those two constants in doing the integral, and you go down and you calculate. It's 1.67 times 10 to the 27th, which is 0.0047%. That's 5 digits things. Similarly, if you take that same ratio using 3/4, because if you're going up, the math sort of has to flip it, and then you apply it at 8/7 for the Pauli pair, because remember, 1/distance cubed to the far side is 2 to the 8th minus 1 to the 8th, because 1's too far away. So you lose that one. So it's 8 minus 7, 8 minus 1 versus 8/7. And then, of course, you've got this anomalous moment, which is for the particle edge, because particles aren't point equations. And you get this 1836.163, which is 0.153 is the experimental evidence. So now you get lifetimes by this method. And when you do elementary particles now, mu mesons, electrons, pi mesons, protons, neutrons, these tau mesons, these omega, the mass value also has a wonderful R² of correlation. That is not just the mass units. You talk about things that have a 1/3 instead of an integer counts. But as you do that, if you take the cube root of it, you get this nice symmetry line. So not just mass units, but also mass values are directly related to each other based upon, well, alpha, which is really the edge versus the equilibrium of the main fundamental forces, and that. Now, of course, because the mu meson used by Yukawa was for a proton-neutron-proton, you again have a 2x force, so 1/2², so it's down by 25%. And when I do that, I get 0.9972 correlation. It is impossible to get these correlations here and these correlations here without there being fundamental underlying physics that gets these things to understand. And if you apply this, we're going to be able to simplify and understand equations without using the abstract alpha fine structure constant, but using actual position in field to understand elementary particles, various constants like gravity and Boltzmann constant, which is the core of Planck's equation and understanding the closed container ideal gas law, but also to understanding what is mass. Thank you.